Buongiorno, morning. Is anybody there?
Buongiorno, sì.
Hello? Can you hear me?
Sì.
No. So what's the problem today? One, two, three. Mi sentite? Buongiorno.
Buongiorno prof, sì, la sentiamo.
C'è nessuno? Non mi pare ci sia nessuno. Proviamo a mandare un messaggio in chat. Allora, dov'è la chat? Provate a parlare.
Ci sente?
Sì, ok, adesso vi sento, grazie. Va bene, era disattivato l'audio. Allora, welcome back to Plasma Physics. We were talking about electromagnetic waves in plasma. So let's go back to what we were deriving last time. Okay, we have electromagnetic waves, so electric field and B field oscillating inside the plasma. And this solution, this wave solution is for transverse wave. So the electric field is perpendicular to the propagation direction of the wave. So we studied the fact that in vacuum, electrons are oscillating in the field of the wave, mainly responding to the presence of the electric field. And we can neglect the magnetic field if we are dealing with a condition where the quivering velocity of the electron, this one here, where is it? Okay, the quivering velocity of the electron is small compared to the speed of light. In this case, we say that we are in the non-relativistic regime, and this is the regime we are interested in our course. Obviously, we go up in intensity, eventually the velocity of oscillation of electron becomes so large that the motion is relativistic, and it needs the full treatment, taking into account the Lorentz force and the effect of the magnetic field of the wave as well. So we set up a system of equation using for the electric field, the source term is the Faraday's law. The source term for magnetic field is the Maxwell Ampere's law. Then we needed a way of coupling dynamically the electric field and the magnetic field to the motion of the electrons. And this is the Newton's law for the electrons. And we added this term, remembering what we were doing when we were studying the electrical resistivity. And this term is crucial for the absorption of the wave, as we will see. And this frequency here is the collision frequency, the term that gives rise to an energy exchange between the electrons population and the ions population. And then we have a constituent equation defining what is actually the current density J that enters the Maxwell-Ampere's law. Doing the maths and linearizing and moving to complex notation, we arrive to a dispersion relation here, okay? This one here. This is the dispersion relation expressed as a function of omega squared, that has, as we can see, two terms. The usual k squared, c squared term, which is present in vacuum as well, and c squared is the speed of light in vacuum. And there's another term which is multiplying the plasma frequency. If no collision are present, so if no plasma is present, actually this term is not there, it's 1. And the resulting dispersion relation is that of electromagnetic waves in plasma, so in vacuum, sorry. And this is the case for a medium vacuum, which is non-dispersive for, actually, no, this term altogether goes away if we are not in the plasma. And we have that in vacuum, omega squared equals c squared k squared. And this is the dispersion relation for electromagnetic waves in plasma, in vacuum. Instead, if we switch on the plasma, then we have this term that has two important components. One, the real part, which we are going to study today, is the propagation. And then we see that there's a complex part to it as well. And this complex part, imaginary part, correspond to the attenuation or absorption properties of the wave during the propagation inside the plasma. So we rewrote the equation in terms of k. So we wrote it as k squared equal the function of omega. And we divided the k squared equation in two terms, a real part and a pure imaginary part on the, and now we were trying to understand how to obtain information on k, the wave number, from the dispersion relation that is expressed as k squared. So we need some complex algebra. And today is, what's today? It's 7, let's put the date up here, 7th of May, 2001. I don't have the phone here. We'll take a break around 9-ish. And so we have that our dispersion relation is expressed as a complex number, as k squared, and we want to go back to k, the wave number. So we call it the real part of k squared as a capital A, and the imaginary part as capital B, and the kr and ki, respectively the real and imaginary part of the wave number, we call it as lowercase a and b. And let's obtain the relation that links A and B. So the components for the k squared and for k. Before that, we said, okay, we have our wave number that can be expressed as two terms, the real part and the imaginary part. So we plug it into the propagation exponent of the solution, or the plane wave solution, and we divided the imaginary part and the real part of the solution in two terms. We see that the imaginary part is an exponential of a pure imaginary phase, and this corresponds to the oscillation and propagation of the wave. Whereas the imaginary part becomes a decreasing exponential if ki is a positive number. This expresses the fact that as the wave propagates along the x direction, which is the direction of the wave, the intensity of the wave, for instance, the electric field, the velocity, the amplitude of oscillation of the electron, the density current, or everything that is connected to the wave propagation is exponentially going down and being damped, or let's say absorbed attenuated in the plasma. Okay. After this brief recap, then let's see what we can do about our project, that is going to from k squared to k. So we can write k squared as a plus ib times itself. This is the meaning of k squared. So we get a squared minus b squared plus I that multiplies to ab. Oh, wrong symbol, sorry. This is all lowercase, because this is k times itself. So we have a squared b squared plus I twice the double product. Okay, and we can identify now with the same color code that this is actually the real part, the imaginary part of k squared. So we call it imaginary part of k squared. And the first term is the real part of k squared. Now, if the real part of k is much larger than b, and this will check in our derivation that actually this is the case, then we can neglect terms of the order of b when they are confronted with terms of the order of a. And in that case, then we can say that the real part of k squared is almost equal to a squared, which is the real part of k squared. So what we call kr squared. So if we want to get kr, this is just the square root of the real part of k squared. And if we go back to what this k squared was, okay, let's take it, is this term here, okay. And instead, if we, okay, let's leave it for now. If we look at the imaginary part, we see that the imaginary part of k squared is equal to 2a times b, which is equal to 2 kr times ki. So we see that if we want to obtain ki, we can just divide the imaginary part of k squared by 2 times the real part of k that we just obtained before. So first of all, in order to obtain ki, we take the square root of the real part of k squared, and then we divide the imaginary part by twice the real part of k. Okay, this is our plot. Let's rewrite what is k squared, so we can go briefly over the terms. So we have k squared was omega squared over c squared minus omega p plasma frequency divided c squared times 1 plus nu squared over omega squared, where nu is the collision frequency and omega squared is the square of the angular frequency of the wave, plus I, and then we have the complex term, which is omega p plasma frequency divided c squared. Then we have nu over omega divided the same denominator as the real part. Okay. So we see that here in front we have this term, And we have that this is the real part of k squared, and this is the, sorry, vice versa. The red one is the imaginary part, and the green one is the real part of k squared. Okay. Now we see that we state actually that we are interested in a condition where nu over omega is much less than 1. What does this mean? It means that the collision frequency, which is the time scale for plasma redistribution of energy of momentum among electrons and ions on. So this is representing the characteristic plasma times or frequency. Is much lower than the frequency of the wave. So we restrict our attention to situation where the wave phenomenon is much faster than the usual frequencies of the of plasma. If you think of a comparison, for instance, collision frequency are of the order of 10 to the 10, 10 to the 12 hertz, usually in the plasma we are interested on, and for instance in MCF, and optical frequency of light, for instance, green light, has an angular frequency of about 10 to the 14, so 100 times higher or more. So this is a good approximation. And by using this approximation, so this for our cases, it's not always true, but we need an assumption, a working assumption in order to derive some relation. We see in that case that if this is a small number, the denominator can be neglected with respect to 1. So these two terms can be neglected at the denominator. And what it remains is actually that the real part of k, so we now do this. This is the real part of k squared, and the square root of this is the kr. So we have the kr equal to the square root of what this one here is omega squared over c squared minus omega p squared times c squared times, and then we have that, as I was telling you, this factor here becomes 1 for our case of interest. So we put it 1 here. So actually this becomes 1 over c omega squared minus omega p squared, square root of it. Okay. Now we have to derive the real part as well, the imaginary part. And the imaginary part, ki, which, if you remember, we find out, let me see if we wrote it last time. No, actually, I don't see it here. Okay. We'll come to it later on. So the imaginary part is equal to the imaginary part of k squared. So is omega squared p divided c squared. Then we have nu over omega. Okay, this is the imaginary part. the denominator becomes one, and ki is the imaginary part of k squared divided twice the kr. So this is 1/2, and then we have kr, which is square root of omega minus omega p squared, and we have that sc comes at the denominator, numerator. Okay. So in the end, we can get rid of 1c squared here, and we end up with we have omega plasma squared times the ratio of the collision frequency to the frequency of the wave. Then there's a factor of 2, and then we have 1/omega squared minus omega p squared. Okay. As you can see, now actually we can verify that our assumption that A, if you remember, A much larger than B is satisfied. Okay, we have, this is A, the imaginary, the real part, and this is B. And if you see here, we have that this factor here, we assume that in our for our purpose, this is a number that is much smaller than 1. So this term actually is much smaller than the first one. So we have that A is actually much larger than B. So the approximation that we were using just before holding in the present case. Okay, so we have that the two parts are responsible. The green one, so the real part is responsible for the propagation properties of the wave, and the imaginary part is responsible for the attenuation of the wave. Okay, so we'll discuss separately the two, starting with the propagation properties. So let's see what are the propagation properties. So let's divide and let's study the propagation. So our dispersion relation is actually something that we can write as, we should go back to the dispersion relation. Where was it? Okay, this one here. And you see that we have k squared on one side and the real part on the other side. Okay, so actually, if we combine the two and we isolate what is the propagation relation, then we can express it as c squared kr squared equals, we just take the square of this term here and go back to the usual dispersion relation. So we get omega squared minus omega p squared, and we can rearrange it in as the usual way, having omega of the wave on the left hand side, and then this becomes omega p squared plus c squared kr squared. Okay, this is the dispersion relation for magnetic waves in plasma. And let's remember that now that we have separated a complex part of K, then Kr has to be a positive number. It cannot be negative or imaginary. is because the imaginary part is contained in the other part of K. So for sure, KR squared is positive. What does this mean? KR squared must be positive. And this means that you can see it here, if this has to be positive, then omega of the wave has to be larger than omega p. So we have to require that omega of the wave that must be much greater than or equal to the plasma frequency. Okay, this is an important constraint. It means that only solution that have an angular frequency larger than the local plasma frequency of can propagate in the plasma. So let's draw our dispersion relation. Okay, so we have KR, and this is the real part of the wave number, and omega. So we identify omega p, the plasma frequency. And let me write it here again. What is this relation? Omega squared equals omega plasma squared plus c squared k squared. Now you remember that we have, this is the typical kind of curved parabolic terms. There is parabolic in around the origin and then becomes straight away from the origin. So for wave numbers going to infinity. And so we have the two asymptotic curves here, one and the other one. And the dispersion relation is actually a function that goes like that. Okay. And we see that omega has to be, let's highlight this region here. In this region, we don't have solutions. So you remember that dispersion relation is telling us which is the space of solution available for wave propagation. And this is this red curve here. Down here, for omega less than omega p, we have no propagation at all. Okay. And let's recall the properties of this plot. For very high k numbers, and which means very short wavelengths, the phase velocity and the group velocity are the same. Plasma is becoming non-dispersive. Light is propagating through the plasma almost as it does in vacuum, because the speed of this wave is here plus ck, and here is minus ck. So we have the progressive part and the regressive part. And for very short wavelengths, the propagation of the electromagnetic waves is becoming asymptotically as in a vacuum. What does this mean? It means that when we go to very high frequency, the high frequency, so short wavelengths, it means going from, let's say, optical radiation to X-ray radiation or gamma radiation. We notice that actually the plasma becomes, in a certain sense, transparent. As you know, we can use very penetrating radiation for going through matter, and we can go with the same principle, go through plasma as well. And in that case, Very short wavelength radiation can propagate at the speed of light through plasma without any dispersion. So it can be used as a diagnostic term. Instead, if we go to wavelengths longer than let's say optical radiation for our plasma of interest, and we go to microwaves or radio waves, we see that lambda is increasing and k is going to 0. And in that case, we see that we approach a region where we don't have propagation anymore. The phase velocity goes to infinity, but the group velocity goes to 0. So we don't have propagation for very long wavelengths. So we recover these properties. So let's see what is the constraint that the omega of the wave has to be larger than the plasma frequency. So we require that, for instance, omega squared must be larger than omega p. And I remind you that omega p is omega pe, so it's the plasma frequency for electrons. Okay, we are focusing our attention on the interaction of electromagnetic waves with the electrons. And omega p is then equal to the charge of the electron times the number density of electrons divided epsilon naught mass of the electron. Okay, and this corresponds to a so-called critical frequency. So let's turn around this inequality, and we get that the number density of the electron has to be smaller than what? A term which is mass of electrons epsilon naught times omega squared of the wave divided E squared. Okay, and this term here is called the critical density, and critical. What n critical corresponds? So n critical, this is called the critical density. At an electron density equals to the critical density, what happens? That the plasma frequency is equal to the frequency of the wave. So we say that a given radiation can propagate up to a certain density, which is called the critical density. At density larger than the critical density, then the omega of the wave becomes larger than smaller than the plasma frequency, and the wave cannot propagate anymore. So we can express the critical density as a function of the property of the wave. So for instance, let's remember that what is the relation between omega for a wave and the frequency and the wavelength. So remember that omega for the wave is equal to 2 pi f, where f is the frequency of the wave, and we can express this as 2 pi c over lambda. And let's suppose that this is the lambda in vacuum. So the wavelength in vacuum. So let's imagine to produce some kind of radiation in vacuum away from the plasma, then the wave encounters the plasma, and start penetrating inside the plasma, going from low density to high density. It will stop at a certain density where the frequency of the wave is equal to the frequency of the plasma frequency. So we can express then the critical density. You see that the critical density is a function of physical constants and the angular frequency of the wave. So we can rewrite the critical density as a function of the frequency of the wave, of the wavelength of the wave. So this becomes as, for instance, 124. The frequency of the wave measured in hertz to the second power times, and this is expressed in electrons per cubic meter. So this is in the International System of Units, a practical formula for defining the critical density. We can express it as a function of the wavelength as well, which is the most usual one. So we can rewrite the critical density as 1,12 times 10 to the 15th divided the lambda, the wavelength of the wave, of the radiation, let's say the electromagnetic radiation, expressed in meters to the second power. And then we get that our critical density is expressed in electrons per cubic meter. And we can go to, instead of meters for the wavelength, to some more practical units, which are microns. Usually electromagnetic radiation is expressed in microns in our studies. So this becomes 10 to the 27, and we have the wavelength of the wave expressed in microns to the second power, and still the resulting critical density is expressed in electron per cubic meter. So let's make an example in order to estimate this critical density and compare it to the other density we know of for inertial fusion, for instance, and magnetic confinement fusion. Let's take, for example, a laser light, a typical laser that we are using in for inertial confinement fusion, and has a wavelength around the optical in the optical window, and you might know that the optical window is about 1 micron wavelength and has a typical energy of 1 eV. So let's take, for example, the neodymium glass laser, which is a kind of high power laser where neodymium rods, like cylinders of large cylinders of glass doped with neodymium, are used as the amplifying medium for the laser phenomenon, so light amplification. And this neodymium glass laser has a typical transition that corresponds to a wavelength in vacuum of about 1,054 micrometers, so 1,054 nanometers. And this is in the near infrared. So our eye actually cannot see it. For instance, a green light is around 0.4 of a micrometer, so 400 nanometers, and this is in the near infrared. And if we plug this number here, so you see that this is about 1 micron, then you see that the critical density for neodymium laser is about 10 to the 15 electrons per cubic meter, or which is the same, 10 to the 21 electrons per cubic meter. Sorry. Is 20 to the 27 here. Okay, we have to use this formula here. So it's 10 to the 20, let me correct it in red, 27 electrons per cubic meter. So this becomes 10 to the 21 electrons per cubic centimeter per cc. Oops. Okay. And this has to be compared to, for instance, the typical density in MCF. If you remember, we had that in MCF we had 10 to the 20 particles, electrons per cubic meter in MCF, and you see that actually the critical density is much, much larger. So optical radiation can go through a magnetic confinement fusion plasma, like a tokamak plasma, whereas we had that in inertial confinement fusion, the typical density is in excess of 10 to the 30 particles per cubic meter, and you see that actually in inertial confinement fusion, we can propagate the laser from outside up to the critical density only. So we cannot reach with the laser, optical laser, the deeper part, the inner part of the plasma in inertial confinement fusion. If we put this together and we want to express, instead of the electron number density as a function of the critical density, mass critical density, so we can define rho crit as the mass critical density. We see that what is rho for a plasma is mass of the electron times the electron density plus mass of the ion times the ion density, number density, which is obviously we can neglect for the bulk contribution to the mass of the presence of the electrons, and just focus our attention to the mass content of the ions, obviously, and what is the mass of the electrons, so we can express the number of the ions and number of the electrons divided the ionization stage, and the mass of the ion can be expressed as mass of the proton times the A number, the mass number of the ion. For instance, for hydrogen is 1, for deuterium is 2, for tritium is 3, and so on. From helium 4 is 4. It's the number of protons plus the number of neutrons, so a baryon number, let's say. So we can express the density of the plasma, the mass density, as A times mass of the proton times number density of the electron divided Z. So we have this factor here, A over Z, And then we have a physical constant, mass of the proton, or proton mass. Let me write it. And if we plug this definition of rho and we express Ne as the critical density, we can rewrite the mass density as 1,86, a practical formula divided lambda 0 in micron to the square times. Then we have A over Z, okay, times nothing. Just this is expressed in what units? This is in kilogram per cubic meter. Okay, so this is another practical formula that, depending on the kind of radiation we are sending to the plasma and the plasma properties, we can establish what is the critical mass density at which the radiation will stop. Okay. Let's consider now another property of propagation, that is the refraction index. So let's move to the refraction index. Oh, time to take a break. Okay, it's 9. So let's take a break and we see each other in 10 minutes. And we'll discuss about the refractive index and the propagation inside the plasma. Okay. Are there any questions? Domande? No? Okay. So let's take a break. Okay, here we are again. Are you there? Can you hear me?
Sì, la sentiamo.
Bene, grazie. Refraction index. What's the definition of the refraction index? We'll use the symbol mu instead of nu, eta, n, or whatever, so not to confuse our notation. Mu is defined as the ratio of the speed of light, c, divided the phase velocity, v phase. So let's remember what is our dispersion relation. The propagation part is omega squared equals to omega plasma squared plus c squared k squared. And let's derive for it the phase velocity and the wave velocity. So we see that phase velocity, v phase, is defined, as you remember, as the ratio omega over k. So omega is the square root of omega p plus c squared k squared divided k, and this becomes c squared plus omega p squared divided k squared square root of it. Okay. Is that correct? Yeah. And remember that K is KR. So let's put it here, because now we have to remember that this is the real part, the propagation of the wave. Or we can express it instead of KR. Actually, a better way would be to get KR as, let's do it like that, maybe it's clear. KR equals, from the dispersion relation, is omega square, omega minus omega p squared divided by c squared. Okay, so we can plug KR inside our relation, and this becomes just, we can factor out a c squared and becomes 1 over square root of omega 1 minus omega p squared divided omega squared. Okay, so if we plug KR inside this formula here, then we can factor out the c squared, and we can write it in this way. And remember that when we have this ratio here, omega p over omega squared, we just define the critical density, and you know that omega p is squared is proportional to NE, where omega squared is proportional to N critical. So we can express that ratio as just in the same way as C divided 1 minus critical, plasma frequency, and not plasma, electron density divided critical density, N critical. Okay, this ratio here can be expressed in terms of the angular frequencies or in terms of the density ratios. And as you can see, this term here is has to be always less than 1 for propagation. So the frequency of the wave has to be larger than the plasma frequency, or the density of the electron has to be smaller than the critical density. So this term is less than 1. So it means that the square root is a number smaller than 1. So the phase velocity actually is larger than c. Okay. So we can say that the phase velocity is larger than c. Then let's derive the group velocity as well. The group velocity is defined as the derivative of omega with respect to k. So we differentiate the dispersion relation, and we have 2 omega d omega on the left-hand side, and on the right-hand side we differentiate with respect to k, so we get c squared times 2k dk. And we can take the 2 factor away, and from this we can recall that d omega over dk equals to c squared times k divided omega, and the ratio k over omega is 1 over the phase velocity. So this is c squared divided the phase velocity. And in our case then, the phase velocity is that one there. So we can write it as, keep on using the same color, c squared divided, we have on top 1 minus omega p squared divided omega divided c. So this goes away, and this becoming c times 1 minus omega squared divided omega squared. And as you can see now, this term is less than 1, and this assures that the group velocity is less than c. So in a plasma, we have that the phase velocity is always larger than the speed of light in vacuum, but the group velocity is always less than the speed of light, assuring the microcausality and all the relation about the fact that the speed of light is the limiting speed in our present known universe. Okay, let's go back to the definition of the refraction index. So now we worked out the phase velocity here, and the refraction index is the ratio of the phase velocity to the group of the speed of light to the phase velocity. So let's write it. Mu, equals c divided the phase velocity. So we can write it as as c divided the phase velocity, which is okay, as we just did, square root 1 minus omega p squared divided omega squared divided c. So there is a ratio of velocity, so it's a dimensional number, and can be expressed as the square root of 1 minus omega p squared divided omega squared, or as a function of the densities, 1 minus the electron density divided the critical density on the square root. And as you can see, this is minus always less than 1. And it's just equal to 1 where we have that the plasma frequency equals the frequency of the wave. Let's rewrite it using the group velocity. So we see that actually the group velocity is equal to c squared divided the phase velocity. So the phase velocity is the group velocity, c squared divided the group velocity. So this is becoming c divided c. Is that correct? Yes. C squared times the group velocity. So this is becoming group velocity divided c, and so that we will use this relation later on. We see that the group velocity of the wave can be expressed as c times mu, or mu times c. So in order to get the velocity at which information and energy travels in the plasma together with the wave, we can just multiply the speed of light in vacuum times the refraction index. Okay, we'll use later on this relation here. So what is happening now? So we can draw a plot presenting the allowed region for propagation and those who are not allowed, the forbidden region, in terms of the refraction index mu. So we can draw a function, the mu, the refractive index, as a function of the frequency of the wave. So we can have the refraction index here. And there's a particular frequency which is important, is the plasma frequency here. And we have that this is called the cutoff frequency. And we see that for, let's write the formula for mu here. Mu equals 1 minus, as a function of the property of the wave, omega p squared divided omega squared, square root of it. So we see that when omega goes to infinity, mu goes to 1, goes to unity, as in vacuum. The refraction index of vacuum is 0, is 1, if you remember that. And when the frequency of the wave goes to the frequency of plasma, to the plasma frequency, this mu goes to 0. So we know that is 0 at omega p and goes to infinity and is a square root, so it goes basically just like that. Okay. So you can see, as you change the frequency of the wave, you have different refraction index. So different propagation properties of different colors of the wave, different frequency of the wave. So is the plasma, we see it behaves like a lens and is an aberrated lens, so it's not achromatic. Actually, every component of the wave has a different refraction index. And we can ban this region. This region is where the frequency, the wave cannot propagate. So this is no propagation. Below the plasma frequency. So actually what we call the way of expressing this, we say that the plasma frequency here is a cutoff, frequency. So below the cutoff, there's no propagation anymore. Okay, so having a given refractive index, the medium is behaving, can refract light waves. So for instance, let's remember what is the effect of placing a lens of glass in a parallel beam of rays. So we have our lens here is made of glass, and we send rays through it. Which are parallel to the lens. Okay. What is happening, the rays that go through the center just go straight of the lens. Then the other ones are refracted at each direction. Not direction, at each surface. So if you remember the Snell law, and you get that the rays are focusing to a point after the lens. So this is the case of glass, and we call this effect as a focusing lens. Okay, and the properties of glass, if you remember the refractive index of a glass, for instance, of Pyrex or a typical glass, has mu, which is larger than 1.2, 1.5, depending on the glass. So it's larger than 1, and you get the focusing behavior. Instead, if you have the same kind of lens, so if you imagine that you could shape a plasma in the form of a lens and fill it with uniform plasma at a given density. This is a Gedanken experiment, so something that actually you cannot do in practice, because plasma doesn't like to be shaped in any form or stay in any form you do. This is the axis of the lens, so rays just go straight on the axis. But what is happening at the interface is, because the refractive index is less than 1, we have that rays are departing away from the axis, and we have that the plasma behaves as a negative lens. So it's refracting rays away from the center. Okay. So this is the plasma case. Here we have that mu is less than 1, and the behavior of the plasma is that of the defocusing lens. Or what we actually call it, a negative lens. So this has important properties with respect to the usual propagation of light, and in matter, in glass, for instance, or in air, or in water, where the diffraction index is larger than 1. So these properties actually combined with the cutoff frequency have interesting application. Let's make a couple of examples of it. So for instance, examples, we make 2 examples of refraction and cutoff. So we can divide the board in 2. We do refraction on the right, on the left. So for instance, let's take our planet. Okay, so we have a North Pole, the South Pole, and we put an antenna here. And in Europe, and we put another antenna on the other side of the Earth. And what we can do is to produce radio waves. So we can have radio communication. So what we do is we produce a electromagnetic signal in terms of radio waves, and the radio waves have a frequency f of about, let's say, 1 megahertz and below. And if you work out the wavelength of this radio frequency is about 300 meters. Okay, so very long wave. These are radio waves. How can they propagate and obviously reach the other side of the Atlantic? So the mechanism is that our Earth is surrounded by air. Let's use air here, obviously. At a certain height, the atmosphere gets very rarefied and becomes ionized. So we get what we call it the ionosphere, where the gas is very rarefied by ionized. So we have a plasma actually in the outer layer of the atmosphere. And what is happening is that the propagation of light waves, these are wavefronts, is deflected by the ionosphere and can go around the Earth, being refracted and reaching the antenna on the opposite side of the Earth, because somehow the ionosphere acts as a wave guide and reflects, not back, but deflects, refracts actually. That's the word we have to use. The waves, so waves are propagating up to the ionosphere and bouncing back to the surface of the Earth. So an antenna can, on the other side of the planet, can collect the signal and send it back. So this is the principle that allows us to communicate using radio wave of very, very long distances. Another example where plasma comes into play is, still we have an atmospheric plasma, but this is something that we are producing ourselves. So let's take the Earth again, our planet, and we have, as before, we have the atmosphere, the outer layers, and then we have the ionosphere here surrounding the Earth. And when we send a vehicle like a spaceship in the atmosphere, then in orbit or to the moon or whatever, we have to communicate with back to Earth with radio waves or some kind of electromagnetic radiation. So we have the antenna on Earth And we have the re-entry vehicle, for instance, for Apollo mission. We had the re-entry vehicle, which is facing with the heat shield the direction of motion, and is coming back to the Earth. What is happening is coming from outer space, so at very high speed, and it will be stopped by the atmosphere. Obviously, the way it enters is not directly like this, but is entering like orbiting in a much longer way. But the concept is that when it enters the atmosphere, it encounters the outer layer of the atmosphere and start ionizing the atmosphere due to the high friction that we have of the high velocity LEM re-entry vehicle and the outer layer of the atmosphere. So we produce a high temperature gas here that eventually becomes ionized, and it produces a plasma just in front of the re-entry vehicle. So when it comes to a much denser part of the Earth, of the atmosphere, it produces a plasma which is very, very dense with respect to the ionosphere, where radio wave can work. And usually our communication with the space vehicles are in the range of very high frequency or ultra high frequency range, which are about 100 megahertz. So 100 times higher frequency with respect to the radio waves. And we have facing the problem of what is called the communication blackout. So this is the re-entry vehicle communication blackout. What is happening, whatever is the frequency range you choose for communicating between the re-entry vehicle and Earth, at a certain point, the plasma produced by the re-entry vehicle in front of itself will go into a region where the local plasma frequency becomes higher than the frequency you're using for communicating. In that case, we'll see that the plasma frequency is higher than the frequency we are using for communication. So we are below the cutoff, and in that region, nor communication from Earth to the vehicle, nor from the vehicle to Earth can go through the plasma layer that the vehicle generates in front of it. When then it slows down, then the friction and the plasma is not there anymore, and so it's just moving gas. It's not ionizing anymore due to the excessive heat in front of it, and so the air becomes neutral again. So there's no plasma anymore, and then the plasma, as if by magic, disappears, and we can start communicating back. So usually these are few seconds or few minutes during which the communication are not possible when we have a vehicle coming back from the outer space. Okay, this is for the phenomena that are connected to the propagation properties of our, where is it, of our dispersion relation. What it remains now is to consider what is happening with the imaginary part, so the attenuation. So let's go to a new page and talk about attenuation property. So this is important. Obviously, we are talking about attenuation where the wave can actually propagate. So we are above the cutoff where the light wave can propagate. And now let's focus our attention on the second part of the dispersion relation. So as we were writing before, let's go and get it back, that formula. Where was it? At the end of, okay, last lecture. Let's take this formula again without rewriting it, so we can comment on the different parts. The important thing is that we have the complex exponent of our wave. We split the exponent into two terms, the oscillating part is the propagation, and now we want to focus our attention on the attenuation. So let's remember, for instance, that this is the way the electric field, for instance, oscillate. So the electric field of the wave is actually an amplitude times a kx minus omega t, where this is the amplitude and maybe a phase, and this is the part of describing the propagation of the plane wave. So if you think about the intensity of the wave, the intensity of the wave is proportional to the square of the electric field. So any electromagnetic wave carries with itself an intensity which is proportional to the amplitude of the electric field. So you see that if the electric field goes as e to the minus kix, which is the attenuation part, then the intensity goes as e to the minus 2 ki times x, the propagation coordinate. And we write this as E naught, for instance, at the end, at a given point, as e to the minus alpha times x. And alpha is called the attenuation coefficient, which is related to the intensity instead of the electric field. So alpha is the attenuation coefficient. The dimension of alpha, as you can see, alpha is the dimension of 1 over a length. And actually, we can call it L absorption or attenuation as 1 over lambda, as the characteristic length over which the intensity of the wave drops exponentially. So you can see this is expressing a fact that given an intensity I naught at a given point, then the intensity drops exponentially as a function of x. So this is an exponential attenuation, and the coefficient of this attenuation is called alpha, the attenuation coefficient, or we can express it the same law as I naught e to the minus x over lambda absorption or attenuation. So what is happening, the wave is attenuated, so the intensity drops. So we say that the energy carried by the wave is absorbed. So we can call it absorption or attenuation. Okay, so if you see, alpha is equal to twice the imaginary part of the propagation wave number ki. So actually, we can write that alpha is equal to twice Ki, and Ki is, I'm copying back from what we had, is, let's go and take it. We had it somewhere at the beginning today. Okay, this one here. So let's take it. And this is Ki. Since we have a 2 in front, we just cancel, take this out, okay? So this is the attenuation coefficient that expresses the way the wave is absorbed and attenuated as long as it propagates through the plasma. So this deserves a highlight. When our derivation is actually holding, so what we have to pay attention to is that our approximation, so the derivation of this attenuation coefficient is valid if electrons are Maxwellian. What does this mean? That basically the derivation up to now, we have used the collision frequency, which we derived for a Maxwellian distribution of electrons. If the electrons are not Maxwellian, are distorted, the treatment becomes a little more involved. So we want to assure that our approximation is valid. So we could say that actually, let's state the fact that they are Maxwellian. It means that the time of momentum, for instance, exchange of energy exchange inside the electron is much faster than the interaction of electrons with the electromagnetic wave. So for instance, we assume that the frequency of electron-electron collision times the momentum content of the electron, typical momentum is mass of the electron times the thermal velocity. And this is the rate at which the momentum is redistributed by electrons within themselves. So we require that this time is this rate is much larger than what? The time that electrons are exchanging momentum with ions, getting rid of the momentum gained by the wave. So this is the momentum of the wave is the quivering oscillation. So mass of the electrons times quivering velocity. So if we require this, it means that actually the electrons will be very fast in reaching a Maxwellian distribution, and on a longer time scale, they will share the momentum acquired by the wave, electromagnetic wave, with the ions. Okay, so we can, as you can see here, we can simplify on both sides the mass of the electrons, and let's recall what the thermal velocity is of the order of kBT over mass of the electron. Okay, there's a factor in front, as we learned. It could be a 3, it doesn't matter, depending on the dimension. The equivalent velocity that we obtained at the beginning of this electromagnetic waves lecture, we remember that the equivalent velocity is proportional to E, the intensity of the Coulomb force, and inversely proportional to the mass of the electrons, the inertia, and the angular frequency of the wave. Okay, and since the equivalent velocity is proportional to E, the electric field, we know that the electric field is proportional to the square of the intensity, and the omega is proportional to 1 over lambda, inversely proportional to 1 over lambda. So the wavelength of the wave. So this is just a derivation of order of magnitude, as you can see. And now we have the electron-electron frequency, if you remember, was something like mu EI equals Z mu EE. So there was a Z factor of of difference between the electron-electron frequency and the electron-ion frequency. They were almost of the same order of magnitude, just that ratio there. So let's put everything together, and we can write in this page, so not to change it. So we have Z, actually, we have mu EI, collision frequency, divided Z, times KBT over ME. And on the other side, we require that we have mu EI times something that goes as a square root of the intensity divided lambda. So we can cancel out these terms here and retain only the trends. So let's take the square of this relation, and we get I divided lambda squared oh no, since omega is the denominator is 1 over lambda, correct this one here, this is proportional to lambda here. Okay, let's put it times lambda. So we have that I lambda squared has to be much less than some constant, okay, it's a number, but the T over Z square, so the dependence of this one here. And T is the temperature of the plasma. This parameter here is called the irradiance for the plasma, and it's telling us that we can apply our derivation if the irradiance I lambda squared is less or equal a constant number, which is 10 to the 14th watt per square centimeter. Okay, if we have at a wavelength lambda of about 1 micron. We'll start again from here on Monday. This is just a constraint that telling us that when we are using laser light that has this typical wavelength, then we can apply all the consideration we've done until now. If the I lambda square, the irradiance or irradiation potential is smaller than this reference value. So we say that if we are below 10 to the 14 watt per square centimeter at 1 lambda, so this is the intensity, okay, at 1 lambda, so for 1 micron square, we say that we are in the collisional regime, and you'll see some more in Azzeni's lecture at the end of the course when we'll discuss about inertial confinement fusion. That's all, folk, for the moment. Are there any questions? Domande? Mi sono perso qualcosa? Se no, ci vediamo direttamente lunedì 8:15. Va bene. Buona giornata. Arrivederci.
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 Arrivederci.